Today we're going to talk about the importance of phase in an image. So this is the context of a Fourier transform. So what we've done here is we've imported a test image from SK image, we've done the camera image, and we're going to take the discrete Fourier transform using NumPy, and we're going to decompose it into magnitude and phase. And I've used an FFT shift and taken the log on the magnitude to make it look nice. We can see that the low frequency components are very high, and let's actually plot a cross section of this and just to get an idea. So we're going to take the diagonal, and we could see that most of the information is stored in the low frequency components. I think the power law, their natural images do follow the power law, and that means 80% of the information is stored in the 20% of the lower frequencies, and that is not what I wanted. I wanted to get rid of the log and just do the diagonal, and we could see that when we take away the log scale that we get something that looks quite ridiculous. But that is just to show you that most of the energy is stored in the low frequencies, but most of the information is stored in the phase of the image. So we can see this with a quick experiment when we reconstruct an image based on magnitude and phase. So let's do this reconstruction right here. And so right here I'm reconstructing the magnitude only, and then I'm doing the phase only, but we need to put this phase in an exponential or a complex exponential right here. So we can see that I use an FFT shift for the magnitude and a log to make it look nice again, but no matter what we do, it's still going to look like garbage because there's no information here. All the phases are set to 0. And for the phase, we get the sharp edges and the lines. It almost looks like the output of a high-pass filter. And this is because of something called phase congruency. So what phase congruency says is that all the decomposed phases in our complex sinusoids in the Fourier domain, when they all align with each other, we're going to get a strong feature such as a line or an edge. So let's look at a quick 1D example of a square wave to see what I mean by this. So I'll link this paper in the bio. So here we have a rough square wave of a certain order in the solid line, and it's Fourier decomposition in these dashed lines right here. We could see it's just a composition of all these sinusoids. And we could see that when these sinusoids are in phase right here, that is that they're all lined up with each other, we get this strong feature, aka this ramp right here that goes up. And we could see that on the way down, they're aligned right here, and on the way down here on this edge, they're all aligned. And we can see in these flat regions that they're all out of phase. So that is what I mean by phase congruency. And this does translate to 2D images, where when the phases are all lined up with each other, that we can get these nice lines right here and edges, and nothing with the magnitude. And just to see the original, this is how we do the inverse FFT. So that's all for this one. Just wanted to show why phase is important, and this alludes to another topic, which is the complex steerable pyramid. So what the complex steerable pyramid does is that it allows us to take local phase and magnitude across many scales, and we're going to see that in the next video.